Welcome back to Big Picture Statistics and Computer Analysis. We want to talk about the two-sample t-test where we have independent samples, and we'll do it for the first example when the population standard deviations are unknown. So basically for this we can have two scenarios. We can have situations in which the variances are equal and the variances are not equal. The standard errors would follow as such with these formulas. And we have a new parameter here called the pooled estimate of standard deviation, indicated by this sigma hat. And our t-statistic, our test statistic, is given by this formula. And degrees of freedom follow if variances are equal. It's n1 plus n2 minus 2. If the variances are not equal, we take the smaller of n minus 1 and n1 minus 1 rather, and n2 minus 1. And we have a nice flow chart here to help us carry out the analysis. So basically, if the standard deviations are known and they're normally distributed, or at least 30, we would use a z-test. We wouldn't use a t-test. If they're not normally distributed, you can't do either a z-test nor a t-test. If both population standard deviations are unknown, then we proceed this way. And let's say they're either normally distributed, the two samples, or they have sizes of at least 30, we can proceed this way. And here's where we have to make the decision. And basically, if the variances are equal, we proceed this way. If they're unequal, we proceed this way. The steps are as follows. We state the null and alternative hypothesis. We have the region alpha. And then, depending on whether the variances were equal or not, we proceed this way. We pick the appropriate degrees of freedom, the appropriate formulas, and we get the critical region based on alpha and the degrees of freedom. Then we calculate the test statistic and we proceed. Now, what we want to do, we want to go straight to a problem and do it straight in SPSS. My videos have been taking a bit long because we run through the procedure without SPSS first. So what we want to do in this, in this video, we want to just do it straight in SPSS. Suppose we want to do this problem here, this one with the teaching methods. Let's read it. Two teaching methods and their effects on science scores are being reviewed. A group of students is taught in traditional lab sessions. A second group is taught using interactive simulation software. The science test scores for the two groups are shown in the back-to-back stem and leaf plot. So here we have traditional method. These are the stems, these are the leaves. For the interactive simulation software, again, these are the stems, these are the leaves. So we have a key here to help us read it. And look what they say. At alpha equals 0.01, Can you support the claim that the mean science test score is lower for students taught using the traditional lab method than is for students taught using interactive simulation software? Whether they told us assume they're equal or not, we're not interested. And the reason being, when we do the SPSS will do both analyses for us. So, what we want to do, let's open SPSS. And while we open it, let me open a new data file for us. We'll open a new data file and we will put these in SPSS. So the traditional lab, let me put in the values. For traditional lab, I'm just going to put in the values right off that stem and leaf plot. So the first value is 64. Second value is 70. 71. 72. 73. 76 twice. 77. 78. 79 twice. 80 twice. 81 three times. 88. 89. 90 and 92. So this is the group that used traditional lab, and what I'm gonna do, I'm just gonna label them as ones. So let me do that for you. Okay, now we are up to the interactive software. So for the interactive software, we have 70, 74, 75 twice, 77 twice, 78, 80 twice, 83, 84, 87, 88 twice, 89 twice, 91, 93, and 99. Okay, now this one is the second group, so I'm gonna label this with 2s. You can use any numbers you wish. Okay, now we did the labeling. Now let me just go to variable view. So these were test scores on science exams. So we'll put these on scale level. We'll call these scores. These we'll put on nominal And these we'll call as groups. Okay, and we will put labels on these. So the first group indicated by the number 1, that was the traditional lab. The group indicated by the number 2, that was the interactive simulation software. So maybe I should just put a capital S on that software. It doesn't really matter. Okay, we entered the labels. Let's go to data. Okay, so we got the groups there. And now we're ready to do our analysis. Let's go to analyze. We are going to compare means. We are doing independent samples t-test. And test variable, we are testing the science scores. The groups is the grouping variable, and let's define the group. So group 1 is indicated by the number 1. Group 2 is indicated by the number 2, just like we did when we created the labels. So let's continue, and let's go to our analysis. Alrighty, so look what SPSS did. It gave us some of the descriptive statistics, and then it generated an output table for the t-test. Now, what we're interested here, we are interested in these. These are test statistics. This is if the variances were equal. This is if the variances were not equal. And what we need to do now, we need to decide whether either of these is in our rejection region. So let me minimize this. Let's go back to our question here. Now again, we're not interested in what they said because SPSS generated both scenarios. So let's take a look here. Alpha was 0.10. If we assume the variances were equal, let's look at the degrees of freedom. If the variances were equal, the degrees of freedom is n1 plus n2 minus 2. So n1 plus n2 minus 2, well, we have to count how many pieces of data we have. However, the SPSS output did that for us. Let's just take a look. See, if we do N1 plus N2, 21 plus 19 is 40. And then if we take away 2, that gives us 38. So the degrees of freedom is 38 as indicated here. So the degrees of freedom is 38. 38 degrees of freedom. What would the critical value be? 38 degrees of freedom and alpha being what did they say? 0.01. So 0.01 with 38 degrees of freedom Oh, and one more thing I forgot. Yeah. Are we doing left, right, or two-tailed? Well, let's see. What was the claim? Two teaching methods and their effect are being reviewed. A group of students is taught. Second group. So let's see. What do they ask us to test here? Can you support the claim the mean test score is lower for students taught in the traditional lab? Now, this was our first group. This was the second group. So if this is lower than this, the difference between these would be negative. So if the difference between those is negative, we are saying that basically the alternative is that mu1 minus mu2 is less than 0. That would make it the left test. So we're doing a left test. So if we do a left test, let's go back to the table. The area alpha is in one tail, 0.01 in one tail. And we got 38 degrees of freedom. So 0.01 in one tail. Yep. Actually 0.01, not 0.10, I'm sorry. 0.01 is here. And we are going down to 38 degrees of freedom. We got it. It's this one. It's going to be negative 2.429. So negative 2.429 is the critical value. Let's look at that test statistic once again. Let's full screen this. The test statistic they had was negative 1.817. That will take us outside of the rejection region. Our conclusion will be, well, our decision will be to fail to reject the null hypothesis. And remember, the alternative hypothesis was our claim, so that means there is not enough evidence to support the claim. That students learn better with computer simulations over the traditional lab. So that's that analysis. Now let's take a look if it was the other way. Let's say we were doing the other kind of test where the variances were not equal. Now, if the variances are not equal, we are going with this and we are taking the smaller of these as the degrees of freedom. So I believe in this problem, the smaller group had 19. The larger one had 21. So 19 minus 1 is 18. So we have 18 degrees of freedom. And the area in the left tail is 0.01. So with 0.01, 18 degrees of freedom, we get negative 2.552. Negative 2.552 is the critical value. All right, let's look at our test statistic. Okay. Our test statistic was negative 1.08, and this one too. This one lands outside of the critical, the the rejection region. So we will fail to reject the null hypothesis once again, and once again, there is not sufficient evidence to support the claim that students learn better in the interactive software labs versus the traditional labs. That's what we conclude. So with that said, both ways there is not enough evidence to support the claim. So we got the same result both ways.